course, the first course. This is LINFO1131. So just make sure you're in the right group, okay? I'm going to teach this course in English, but vous allez me poser des questions en français, dans la langue de Molière, and I maybe will answer in the language of Shakespeare, even though I'm not as good as writer as Shakespeare. Okay, so let me start the course. This is a course, the official title is Concurrent Programming Concepts, but in fact it's more an advanced programming concepts course. So I'll first explain the organization of the course and the grading, and then today I'm going to give a refresher, because this course is a follow-up to the previous course, which is LINFO1104. So we're going to go a lot farther, deeper into many of the things we started to see here. And so I will explain that today, and I will give you a refresher today of this previous course. So if you forgot this one, hopefully after today you will remember again, okay? So the course, there will be, so I am Peter Van Rooij, I'm the teacher. There is going to be one teaching assistant, Tanya Sprokeus. And there are 4 tutors for the lab sessions. Sébastien, Amonix, Nicolas Lowe, Guillaume Jardin, and Raphaël Metz. So the lecture will be on Wednesday. There are 3 lab sessions per week that are planned. Monday morning and Tuesday afternoon. It depends on how many students are enrolled. In fact, I don't know yet what is the total number of students. I see there are 40 students on the Moodle, but the first week I don't really know. I will have to wait until there's the official list. So there are 3 lab sessions per week. So normally you should attend 1 lab session every week, and the labs start next week. Okay, so next Monday and Tuesday. The first lab session is Monday morning at 8:30. I know this is very, very early, but it would be very nice if some of you would be there. Okay. And let me also explain how now the course will be graded. So there is going to be a project in the second half of the course. This project is mandatory. You have to do it during the semester, okay? And it's done in groups of 2, and there's plenty of time to do it. So normally, I expect most of you to get very good points on this project. There will be also a midterm, which is worth 1/4. This one is optional. You don't have to do it, but if you do it, I highly recommend that you do it. And if you do it, it can give you an advantage for the final. There will be a final exam, which is, you write it this way, is worth 3/4 of the points, but it's divided into 2 parts. So the first part corresponds to the midterm, and I will give you the maximum of both. That means if you do very well on the midterm, you don't have to do this part, and only this one. In fact, if you do very, very well on the project and the midterm, then you have already succeeded in the course, okay? And the final thing is there is a bonus. If you attend all of the lab is attend the lab sessions and pretend to be doing exercises. It's not much job. So if you attend all the lab sessions, you will get 1 extra point on the exam, so we'll take attendance. This is a dividend, so this might seem like a funny present that I give you, but in fact, I have a very good purpose with this, because if you attend the lab sessions, then automatically you will understand better the course and you will get better points here. So this has actually a double effect. Okay? So this, in my experience, works very well, and people who do honest work usually get very good points in this course. Okay? So let me now give you some more information on the organization, the course. So there will be slides on the Moodle. So every week you can join the slides. Before I continue, I want to pay a few seconds of respect to the Ukrainians who are fighting for their freedom and also for Europe's freedom. Okay. So I gave you a little bit of information on the course organization, the TAs of the course, the tutors, and what I'm going to do now is explain a little bit the theme of this course, and I will give you today a refresher of the previous course. So in one session, I will try to fill up your brains again with what we saw in the previous course. Okay? Okay, so here is the organization. So this repeats a little bit what I said on the board. So notice there's a Moodle, so please enroll in the Moodle. People who are not enrolled in the Moodle, enroll in the Moodle. Everything is there, all the slides, announcements, project information, and so on. The midterm will be around week 7, probably during the Smart Week. There is this special week that was invented in the faculty around week 7, where there's nothing, but it's a week where people can put things, so it tends to fill up with many things during the course, the things that cannot be done in other places. So probably the midterm will be done there. That's how the course is organized. So the rest I already explained. The midterm, the project, the exam, and the 1-point bonus. Okay. In terms of software, we will be using 2 programming systems. So the Mozart system, as you already know and appreciate from the previous course, Mozart 2, but also we will be using the Erlang OTP system, which is freely available at erlang.org. We will be studying how to build resilient, robust software that doesn't crash, and Erlang is the best system for that that exists. Nothing is better than that. Okay. Let me say a little bit about what we're going to, the themes of this course. So there's a couple of themes that we'll be going through the whole course. One of them is concurrent programming. This already started in the previous course, but we'll go a lot farther in this course. So concurrent programming is very hard because there's nondeterminism. So we're going to show many techniques for making it easy. So that's the first thing. The second theme is declarative programming. This is based on functional programming. This is programming without mutable state. So basically without time. So this is a very curious idea, but it's very powerful. And this is the best way to program. And more programs are being declared. So this will, in some sense, prepare you for the future. Okay? We'll try to do this as much as possible. And the third theme is non-declarative programming. This is programming when you interact with the real world, when you have real world time and non-determinism. So this is much harder, but we will try to make it as easy as possible. So those are the 3 main themes. And to be a little bit more specific, so we have here in the red box You see declarative programming in the black box, non-declarative. Each of the little boxes inside is a programming paradigm, it's a way of programming. So in declarative programming, we see sequential functional programming. Last, in the course 1104, we already saw a little bit how to do deterministic data flow, which is a very nice form of concurrent programming. But in this course, you will see two more paradigms. Lazy evaluation, or by-demand evaluation. This is a very powerful form of declarative programming where the program kind of executes in the opposite direction. So you will see it's a very interesting way of thinking. And finally, we will combine these two into lazy determining data flow. So this is the most powerful paradigm for declarative programming. Okay? And there's many things you can do. So we will see functional, more on higher order, lazy, concurrent, semantics, and advanced algorithm design. Something we did not see at all in the previous course. How to make efficient declarative algorithms. Okay? And then in the second part, we will go to non-declarative programming. So this one, the red one, you cannot do everywhere. Unfortunately, you can't do that all the time. Sometimes you need to go beyond when you interact with the real world. So we'll see that. We'll see how to reduce the non-determinism. So there's a kind of evil demon in there called nondeterminism. So we'll see how to minimize that. We'll see how to do multi-agent programming, and we'll see a lot on how to build robust multi-agent programs in Erlang. So Erlang, which is a language which is based on multi-agents talking to each other with no sharing. So the agents are basically communicating, sending messages to each other. But on top of this, Erlang has built a whole structure of how to build applications. So when an agent fails, when it crashes, the others do not crash, but they can be informed. So they see that this one crashes, and you can use that to build very robust programs. So Erlang has a concept which is called supervisors. So we're going to see how to program and use supervisors. So we will have several lectures on Erlang. And Erlang has a kind of programming pattern structure called behaviors. So all of the complexity of supervisors and fault tolerance is hidden inside the behaviors. So that means the programmer can build robust applications very easily. So the most robust applications that exist in the industry today are built in Erlang, even if people don't advertise. So for example, there is many games have Erlang built inside them, especially multi-user concurrent games, like Call of Duty. Millions of users, has a huge Erlang-based infrastructure. So I'm going to give a talk, an industrial viewpoint for Erlang. So a company called Demonware, which has built a lot of Erlang support for gaming. So we're going to learn about how they use Erlang. Okay, so that's going to be a big part of the course, building robust software. And finally, we're going to look at the more shared state form of non-declarative programming, locks, monitors, and transactions. So when you have a mutable state, like a database, lots of data, but many people are accessing it concurrently, how do you make sure that they don't mess things up? So for that, you have a concept called a lock, and then you have other concepts called monitors and transactions. So transactions are very good. Monitors are really nasty things. Monitors are very nasty, but they are still used a lot. So they're still used a lot. Legacy, okay? So I would recommend you use monitors, but since you will see them in the legacy code, so Java uses monitors a lot. But monitors is actually a very bad way doing concurrency, but you will see it anyway, because it's used a lot in legacy code. Okay? So, the schedule, it would be approximately like this. So the course would be kind of divided into two parts, declarative and non-declarative. So the first week, so S1 is semantic comma, so the first week will be today's the refresher. Then we will talk about, next week we'll talk about lazy evaluation. So immediately we go into lazy and lazy deterministic data flow. And this is a very rich area. Then we will talk about declarative concurrency, and I will give you really the semantics of it. And then we will talk about the advanced declarative algorithm design. These are very sophisticated techniques for building declarative algorithms that are very efficient. You want algorithms that have very good time complexity, and this shows how you can do that. And then we will end with the limits of declarative programming. And then we go into non-declarative programming. So I will continue on data abstraction. So you saw some of it already in the previous course on multi-agent programming. But then we will talk about robust multi-agent programming in Erlang. So we have 2 lectures which are based on Erlang. So I gave already an introduction to the Erlang in the previous course, but we're going to go much deeper into that in this course, okay? And then we'll talk about shared state, concurrency, locks, tuple spaces, monitors, transactions. So the only really useful concept here is transactions. This is by far the most useful shared state concept, but it's important to understand shared state because it's used a lot still, okay? And in the final lecture, I will review some of the more difficult parts. The midterm will probably be in week 7. It will be somewhere in the middle. So the midterm will typically, the topics will be just the declarative part. It'll be on declarative programming. Okay, so that's kind of how we're going to structure the course. Okay, so what I want to do now is refresh the previous course. So I'm going to give you very quickly many of the concepts of the previous course and with code. So as you know, I love to write little pieces of code during the course, so I'm going to keep doing that. Okay. Okay. So this is a refresher. So normally you have seen it already, but I understand students. I know the students that maybe they don't remember some of the things. It's so long ago, last year. But I will assume starting from next week that this is all something completely, you perfectly understand. Okay? So the first 2 lab sessions will be bringing you back to all of the stuff we saw in the previous course. Okay? Okay, so let me start now, giving you the refresher. So the first point is functional programming, okay? And I'm going to give you some different examples of that. Functional programming, where you define mathematical functions in higher order. So I will show you many examples of that today. So this is by far the best paradigm for testing, maintenance, improving correctness, and it's used a lot now. When I started teaching these courses 20 years ago, it was not used so much. So I was telling people this is so good. People are saying, well, yeah, but why is nobody using it? But that has changed now. By nowadays, it's much more used. Even Java has, the JVM has a more functional language called Clojure built on top of it. And many of the cloud analytics tools are based on functional concepts. So if you take the cloud computing course, which is a very nice course, I recommend, you will see some of these analytics software platforms. And if you look carefully, you will see that they are mostly functional, actually. Or they are mostly deterministic data flow, kind of concurrent kind of function, okay? So that it's much more used today because it's the only way to write large, reliable concurrent programs. Okay? So in this course, we're going to push the functional programming as far as we can, as far as I know how to push it. Okay? So you'll see a lot of things on functional. So the deterministic data flow, but especially the lazy form and the advanced algorithm design. Okay? So that's basically the idea of functional programming. Now let me go into some specific topics. The first one is invariant programming. You remember invariants? Invariants are important for loops. Okay? Taylor recursive functions are the same as while loops. And so let me give you then an example. So if I define a factorial function, if I say something like this, if n is equal to 0, then 1, else n times factorial n minus 1. Okay, so this is a nice factorial function. And you can use it to do computations. Okay, so here is factorial of 20. Let me make this one a little bit bigger. Okay, of course you all know, you remember, that this is not a good way to write factorial, huh? You remember that? This is actually a very bad way of writing factorial. Do you remember, you know why? Why is this bad? It's not Taylor recursive. And what does that mean actually in terms of the execution? What's going to happen? What kind of bad thing will happen during the execution? Big memory. So the stack size will grow, and in fact is proportional to n. And the reason is that the function call, the recursive call, is not the last call. So what you really want is to make this thing Taylor recursive, which is the function call is the last one. This corresponds exactly to a while loop. So doing it like this, here you have an explicit need for a stack. N times factorial n minus 1. When you do the recursive call factorial n minus 1, after that call, you come back to do the multiplication. That means during the call factorial n minus 1, this multiplication has to be in memory, okay? And because it's recursive, n times n minus 1 times n minus 2 times and so on. They're all in memory. So if I do factorial 100, then the stack will be 100 levels deep. Okay? So this is not good. And especially will not be good when we start writing concurrent programs. In a concurrent program, this will be a function will turn into a concurrent agent. And a concurrent agent runs forever. Okay? It keeps taking input. But if the stack size is growing, it doesn't work. Okay. So this is actually a completely wrong way of writing it. So the right way, so here, let me write it now another way. I add an argument. So I corresponds to the n. A is an extra argument called an accumulator. And now I will do some kind of magic. If I is equal to 0, then I return A. Otherwise, I do a recursive call, and the arguments are I minus 1 and I times A. Okay? And if I do this, unless I make a mistake. If I make a mistake, you have to tell me. same result as before. So I have two arguments. One is called the argument is called an accumulator. It accumulates the result, and it accumulates the result before the recursive call. So you can see this is a tail recursive program because the recursive call is the last operation. Now the question, how do you write these programs? It's kind of magic. The way to write them is by using invariants. Okay? The way to write them is to take the result, is to write a formula. To take the result, which is n factorial, and to divide it into two parts. So in this case, it's easy. I factorial times a. N is the argument of the function, so n is a constant in this equation, whereas I and a will be changing. You will have different values of I. So the idea is you will try to reduce the value of I and increase the a. So it starts like this. If I is equal to n and a is equal to 1, then this equation is true. Okay? And then we decrease I, n minus 1, and here we make it n times 1. So if I is equal to n minus 1, and here we have a is equal to n times 1, the equation is still true. And we keep going, decreasing until this one is 0. 0 factorial is equal to 1. And then this will actually be, the number here will be equal to n factorial. So the idea is that this equation is always true. And this automatically gives you a tail recursive function. Okay? So we're going to do more complicated loops and declarative programs in this course, and the right way to write them is by doing invariants. Okay, so this is a refresher, huh? We saw this before, huh? And sometimes the invariants are very useful. We will see examples where the invariant is really the only way to write the program. Okay? So here's then the code. So in the left I give code in C or Java. So here you see a while loop, and A and I are the two arguments. While I bigger than 0, A becomes I times A, and I decrement I. So you see I'm changing both A and I. In the functional case, A and I are arguments here, okay? And I'm doing exactly the same thing. The A argument becomes I times A, and the I argument becomes I minus 1, okay? And when I'm done, when I is equal to 0, then A will be the result, okay, here. So these two programs will basically execute in exactly the same way. And so here you can see that A and I, that the memories used on this in the C code is constant, okay? Because I just have two variables, A and I. The same is true here. Because it's tail recursive, this recursive call is actually going to reuse the stack frame. So A and I will be stored in the same place as I times A and I minus 1. Okay. So these two are doing exactly the same. So what's the difference if they're doing the same? The difference is that the second one is actually obeying the semantics of functional programming. It's actually declarative, whereas the first one is not. Anybody can assign A, where here I'm actually defining a mathematical function. So the second one, I can actually use it in a concurrent way, and it will not make any bugs. There will be no race conditions, no nondeterminism. So even though they're doing exactly the same thing, the second one is actually better because it's declarative. It's obeying the lambda calculus. Okay. So remember we saw lambda calculus in the previous course. So remember that the people were trying to get their brains around the lambda calculus. So the lambda calculus, which is the core of functional programming. So you will be happy to know that we're not going to see lambda calculus anymore in this course, but it's important to know it because it's the reason why functional programming is so useful. Because it obeys something called the Church-Rosser theorem. This very simple calculus will give you the same result no matter how it's executed. Okay? So the program on the right is a lambda reduction, whereas the one on the left is not. The one on the left is using mutable state in a very disciplined way, but nobody is guaranteeing that. Okay? If I make a mistake on the left, then I can mess it up. Whereas on the right, I'm not using mutable state. It's a perfect lambda reduction. Okay. So this I'm saying this to refresh your memory. So remember, we saw lambda calculus. So I'm not going to repeat the lambda calculus in this course. It's not a theory course. We don't have, unfortunately, time to go on. But all of the declarative programs that we do will, behind the scene, are still with lambda, okay? When we do lazy deterministic concurrency, it will still be doing lambda calculus. Okay, so that's the invariant. So when we do loops, we will base on invariant. So this is a general rule in all languages, in all paradigms. If you want to do a while loop or a tail recursive function, which is the same thing, you have to write down an invariant. And the right way to code is to start by writing down an invariant. Okay, so that's one thing. Let me go on now to refresh. The next thing you saw is called higher order programming. Okay? So in higher order programming, the idea is that functions are just values in the language. They are data, like numbers or records or lists, okay? And you can define a function anywhere, and when you call that function, it will always behave in the same way, okay? So higher order programming is the concept underneath all data abstraction. So you will see many, many data abstractions in languages, in different kinds of languages. So there's a fairly new one called Golang done by Google, there's Clojure, there's Rust, there's all kinds of new languages. And they will be defining data abstractions. All of these data abstractions are based on higher order programming. Okay. So in C++, you have classes, metaclasses, templates. Well, that's just higher order programming, okay? It's all higher order. So let me refresh your memory on that. So let me write again a piece of code. So if I declare, for example, n is equal to 5, and I have a function, add n, x plus n. In this function, when I define this function, add n, you can see that the n here is not an argument. Okay? So what is it? Well, the n exists in the scope of this function. So when I define this function, the n is defined, okay? So this gives me 16, which is 11 plus 5. Now I can make this general. So I do make add, and this make add function will return a function. So here I'm doing real high order programming. The make add here, the n is not an argument, And instead of defining this function add n directly, I define it inside of make add. So the dollar is just to make it anonymous. There's no identifier. So this is just a value, okay, which is the return value of this function. And this function will take x and do x plus n. So again, n exists in the scope here, and it's going to be there. So each time I call make add, I will create a new function. Okay. So this is a typical kind of example of higher order programming. If I do make add 5, I will create a function called add 5. I will do make add of 10. I will do a function called add 10. Okay? So the same make add call will let me create different functions. Okay, so add 5 returns the argument plus 5, and add 10 returns the argument plus 10, 16 and 21. So the way it works is that function values are actually not just data structures. There is something dynamic about them called the potential environment. Okay? Okay, so one of the concepts we saw in higher order programming is the order of a function. Here I'm calling it add n. I've called it make add in the example code. So the order of a function that takes arguments that are not functions and returns something that's not a function is a first order function. And a function that takes a first order function as argument or returns a first order function is second order. Okay? So the order is a way of quantifying how abstract the higher order programming is. So here, for example, add this function add n, which returns the function. So what is the order of add n? You tell me. Someone else. I know some people know the answer, right? 2. 2, yeah. So the order of add n is 2. You see that? Because add n returns a function that takes x and does x plus n. So it returns a function that takes a number and does an addition. So the function that it returns is first order, so add n is second order. Okay? So this is a second order function. Okay, see how that works? So if you do, for example, object-oriented programming, and if I have an object that does computations with integers, then creating that object, there's a function new, which takes the class and returns a new instance. New will be a second order function, okay, and you can define it in higher order. Okay, so a little bit of semantics. So this concept, the function is a value, is really very important, and you will see it everywhere. And there's many names for this thing. I call it a procedure value because in the kernel language we have only procedures. So I called it in last year's course. I called it a procedure value. But typically this concept is called a closure. In French, une fermeture. Closure, because it closes. So it's a mathematical term because it has its own environment, which is created when the function value is created. Okay, another way of calling it is a lexically scoped closure, because when you create the function value, you look at the identifiers that are lexically, so textually, in that are defined where you define the function. So another way, a synonym is calling it a lexically scoped or statically scoped closure. So you will see this term all over the place. People love talking about it. So it's a very fundamental concept. So we saw the semantics of this. Just to remind you, remember in the previous example we had add 5 and add 10. Here, semantically, let me give you just a little bit of semantics. There's a variable in memory, A1, which is bound to the add 5 procedure, and this one has 2 parts. It has the code here. So in the kernel language, the code is actually a procedure because it adds an extra argument for the output. So r is equal to x plus n. R and x are arguments, but n is not an argument. N is defined in its own special environment. So the environment connects the identifier n with a variable in memory. So this little variable, little n, will be equal to 5 for A1. But we also defined add 10. And there's another variable, A2. And the environment here will refer to another variable, little m, which is bound to 10. Okay? So this gives us 2 different closures. Now this is the semantics. So the left, it has 2 parts. The left part is the code. So in the actual implementation, this will be machine code. This will be instructions. And the environment frame will basically be a vector of pointers to variables. Okay? But semantically, this code is defining this procedure. Okay? And semantically, the vector is an environment. Okay? So whenever you implement a language, an object-oriented language, for example, you will have this kind of structure all over the place. Pairs where you have code and an environment, a vector of variables. Okay? So this is a very important thing, and we're going to keep using it. And functional programming is based on this. And all data abstraction is based on this. Okay? So this refreshes you. So this is all very clear, right? You remember it all, huh? This, Yes. Say yes.
Yes.
Yes. Good. Thank you. Okay. You can always interact with me, huh? If you don't agree, if you have some comments, you just say, huh? I prefer that you're more active, huh? So here's another example. This one, map, is an important higher order function. This one has 2 arguments. It has a list and a function, f, which is a 1-argument function. And notice here we're using case. So I will talk about symbolic programming later. When I'm traversing now this list, L, and the end of the list is nil, otherwise the list has pairs. So basically, I'm applying the function to every element of the list. Okay? Now, the recursive call here, I'm creating a new list. So L is an input list, but I'm creating an output list, and I replace the value h by f of h, and the vertical bar is the list creation operation. It takes an element in a list, and builds a new list from them, and I have here the recursive call. So this might look like it's not tail recursive, but it is tail recursive. Do you remember why? So this function map is a tail recursive function. Okay? Do you see why it is? Do you remember why it is like that? Remember the factorial, let me go back. I don't have it here, but it's in the code here. So this one, on the top here, n times factorial n minus 1. So after the recursive call, I still have to do multiplication. So that's not tail recursive, huh? But in this one, in the map case, it is. I'm doing the recursive call to map. And after I do that, I will build the list using the vertical bar. It's not multiplication, it's building a list. So it's a data structure construction. So unlike the factorial, this one is tail recursive. Okay? You remember why it's like that? Does anybody remember why it's tail recursive? Yeah?
There's no hanging operations.
Sorry?
There's no waiting operations.
There's no waiting operations. Why is there no waiting?
I mean, the list is just the next like value.
Yeah, that's right. But so you understand, but there's a small yeah. So you're right. There is no waiting operation. But why is there no waiting operation? So let me explain. Okay. So I can see that it's not always clear. So this map function is actually a procedure in the kernel language. L, F, and it has a result. Okay, a function always has a result. So semantically, that result, we make it visible in the kernel language by making this a procedure. And here we have R is equal to FH. TF. Okay, so this result is equal to this. Now, let me write this in kernel language, and you will see why that it's tail recursive. Okay? So, the function f, let me say it's doing x is f of h. And then there's map. Let me do like this. T, F, R, R1. And then I have R is equal to X bar R1. Okay, so this is the naive translation. I'm calling F, I'm calling map. So this one returns X, this one returns R1. And then the R is equal to X bar R1. So it seems like this is done after. But it's not. So this, you can actually do it before. And I will explain why. You can say R is equal to X bar R1, and you can do the map quality as the final call. So I'm actually defining R and X1, so let me define them. So I call f of h, returning X. I create the list R, but R1 is an unknown variable. So I can create the list even though I don't know the value of R1 yet. And then I will bind it in the recursive call. So this one is tail recursive. The reason why it works is that I have these unbound variables. So this is the notion of a single assignment variable. Okay? This allows the map to be tail recursive. Okay? Because I can create data structures that have a hole in them. So this unbound variable, it's kind of like a hole, a trou, and you fill in the hole later. And it's still declarative because you can only fill the hole once. Once it's filled, it's filled. You cannot change it. So it's still declarative, okay? And this is very important. So it makes map tail recursive. But as we will see, it will allow us to do declarative agents, concurrent agents. So this notion of single assignment lets us turn the map into a concurrent agent. So remember how concurrent agent works? So you have the map, for example, running in its own thread. Now I'm going a little faster. The L is an input stream, and then you have another one which is the output stream. So the list turns into a stream, because the elements are created incrementally, and the output stream is also created incrementally. So I have a concurrent agent taking stream of input and returning a stream of output. And it all works because of single assignment, okay? The agent the map is still recursive, and what it means is that the memory used is constant. It has to be constant, otherwise it's not going to work. Okay? So you can see that we add single assignment. So this is a fundamental concept in concurrent functional programming. Okay? It allows building declarative agents. So we're going to use them a lot in this course, as you will see, and we will do many things with these declarative agents and single assignment. Okay? So it's like assigning a variable where you can only do it once. So you can see it's like a restricted form of state. Okay? It's restricted so that it's declarative. It's not like I can assign many, many times, which is very nasty because you can always assign again and break something. Here I can only assign once. So doing things once is good if you only do them once. Okay? So this is, it seems a very simple thing, but it's a very fundamental concept. Okay? So let me go on now. So we saw many other things for higher order programming, and I'm not going to show them all now. We saw genericity. Genericity is when a function takes a function as input. Instantiation is when a function returns a function, like when you create a new object. The new function in an object-oriented language is returning an object which is actually a function, an object which is represented by a closure. So that's a case of instantiation. So this is used all the time. And then we saw other examples, composition. We saw a very important higher order function called fold, which allows hiding an accumulator. I'm saying it's abstracting because from the outside you don't see. It's hidden inside the fold. So conceptually there's an accumulator, but you don't see it. So the fold lets you hide an accumulator. Also we saw encapsulation, remember, which is important for data abstraction. We also saw delayed execution. I take a statement, I make a function out of it, and I give this function to someone else, and when you execute the function, then you execute the statement. And it's like execute a statement in its original place, only it's done somewhere else at another time. So with that, you can build control structures. So really, higher order is a very powerful fundamental thing. Okay. Okay. Let me go on. So the next thing I want to talk about is symbolic programming. But let me make a small break now. So let me talk now about symbolic programming. This is another thing we saw in the previous course. Symbolic programming is programming with things that are representing a kind of, that are not just numbers, but structural things. For example, one of the important data structures we saw is called a list. And we saw the way to define it using a grammar rule definition. So this is a recursive definition. A list here is defined as either being nil or, so the vertical bar in the grammar means or an element E followed by a vertical bar. In quotes means it's a part of the definition of the structure we're defining, and followed by another list. Okay? So a list is a recursive structure that ends in nil. Okay? So this is one of the most fundamental symbolic structures. It was first introduced by the Lisp language in the 1950s, so it's a very old thing. But it's ubiquitous, and it's a very important structure. And many languages are giving syntactic support to this. So A bar, B bar, C bar, nil. In Oz, there's many ways of saying the same list. You can use the brackets, the crochet, to denote a list. Or you could represent them as records, completely explicitly, where the vertical bar here is the type, and you have the first argument is the element, and the second argument is the recursive list. Okay? We saw the graphical representation of this, so you can represent these structures as trees, basically, but a list is a kind of degenerate tree where it's going down in the right. So here, this is the list 1, 2, 3. So the vertical bar is the root, the leftmost branch is the element, and the rightmost branch is the sublist. Okay? And then we can do an operation called pattern matching, where we take this data structure and we compare it to a template, which is called a pattern, and we will then assign the identifiers in the template to parts of the data structure. And there's a special instruction called case that lets you do that. So languages that do symbolic programming, like Haskell or Erlang or many languages doing symbolic programming, will let you do pattern matching. Okay? Will let you take apart these structures. So if I do case L of H bar T, then I will, H bar T is a pattern, which is a kind of picture, a template, and I match it to be an actual data structure. So L is the actual data structure in memory, this part on the left, and I'm matching it to this template. Okay? And if it matches, you can make it correspond, then you will bind the identifiers. Here H and T. So H will be equal to 1, T will be 2 bar, 3 bar, nil. But it might not match. If I match this with nil, for example, it will not match because nil does not match with the vertical bar. Okay? And now, because now we're talking about lists, let me show an important operation. So I showed already map as introduction, but now we go a little bit farther. Let me show you the fold operation, because it's a very important operation. So it's using a higher order programming, and there's an accumulator inside. And the way it works is that if I have a list, A0, A1 to A-n-1, and a function, f, I can define repeated application of the function. So, for example, if I do something like this, if I have a list 1, 2, 3, and the function is addition, and I start with the identity element, I can repeatedly apply the function. So this is a binary function, starting with the identity and applying all the elements of the list. Okay. So this will be what the fold operation computes. Okay. So it has 3 arguments: the list, L, the binary function f, and the identity element u. Okay, to start the computation. So you can define it easily. So this one is called fold L because it's left associative. There's another one called fold R, which is right associative. So the left associative one is the most commonly used one. So here I'm doing pattern matching. So if L is nil, then I return U. Otherwise, I will do one step. So the U becomes f of UH, and I do a recursive call. Okay? So let me show you how this works. Fold is a very important function that occurs in many, many places. You'll see it appearing very often. So L, U, L, F, U. L of nil, then comes U. Otherwise, H bar T, fold L, so T, F doesn't change, and instead of U now, I put the one step of the operation, so the binary operation F, U, H. Okay, so this is the fold operation. So you see it's accumulating. So the U argument is actually an accumulator here. It's like the A in the factorial definition. Let me show you an example. So I can do browse, fold L. Let's do 1, 2, 3. Let's do the function here. X plus y, and it starts at 0. So here we have the three arguments, the list 1, 2, 3, a two-argument function that takes x and y and does x plus y, and the identity, the beginning element 0. So this is going to add up all the elements and returns 6. Okay, 1 plus 2 plus 3. And of course you can do many variations of this. Here's another variation. Instead of addition, I do multiplication. Now we will start with 1, and then do 1 times 1 times 2 times 3. What do you know? It's all so equal to 6. Huh? Show you an example. Let me add another 1. So the addition will return 10, and the multiplication returns 24. Okay? So the red, question in red. So is fold a tail recursive function? What do you think? Is fold tail recursive? What is the last operation? What is the last operation? Isn't tail recursive? Yes, huh? Yes, I see someone nodding their head. Yes, it's tail recursive. So this is fine. It turns out that when we start building a declarative agent, a concurrent agent, that takes messages and it has an internal state, okay? And each time a message arrives, the internal state is updated. So that's usually how an agent works. That receives messages and it does some kind of computation, updates the internal state. The fold is exactly the heart of this, because the list coming in is a stream of messages. The F is the state transition function, and the U is the internal state of the agent. So this fold operation is actually the heart of a concurrent functional agent. It's interesting, huh? And there's other uses of fold. If you look at cloud analytics tools, there's a fundamental operation called MapReduce. Well, reduce is just a synonym for fold. So the reduce operation takes a whole bunch of new things and combines them together. So the fold basically takes a list and reduces it to a single element. For example, by taking the sum, or maybe it does statistics. Maybe these are data items that you're doing a big data analytics, and you're doing some kind of statistics on them. Well, the fold operation F, maybe it's doing the statistics. It's computing the mean and the variance, for example. So the fold operation is really very fundamental. Okay? So we will see it more in this course. Okay, let me go on now. Let me now talk a little bit, refresh your memory on data abstraction. So we saw already a little bit about data abstraction in the previous course. So data abstraction is built on top of higher order, and it's a fundamental thing in computing technology, okay? So it takes a piece of program and puts it in a box. And you can only access the internals through the interface, okay? So if I have a program, I have here a box, I have stuff inside, and I have an interface. And the only way to access the internals is by going through the interface. And this interface obeys certain rules. If you don't obey the rules, the interface will not do the work. Okay, you have to follow the rules. For example, if you're building a stack, you can push and pop, but you can only do a pop if there is an element. So if there was previously a push. So that's a rule that the interface obeys. Okay? So all large data programs are built using data abstractions. All programming languages support it. And the three main advantages are that the interface guarantees that the functionality works, because you are forced to obey the rules. Also, it reduces complexity. The programmer can use the abstraction without knowing how it's built. Okay? So that means in the mind of the programmer, it does not have to understand the whole program. So you can build programs in teams, and that's the third advantage. You can divide a large programming task into pieces that are done by teams. So this is what makes computing technology practical. Without data abstraction, we would not have the computing technology invading society and the way it's doing today. Maybe you think you can say whether that's good or not, but it's made possible by data abstraction. Okay? Okay. The main basis of data abstraction, well, is lexical scoping and higher order programming. So lexical scoping guarantees that data can be hidden inside something. So if I do local X in a piece of program, the X can only be accessed in between the local and the end. So this is a lexical concept. Lexical means it's related to the text of the program. Okay? And building data abstractions means you need to build these interfaces. So the way that's done is using higher order programming. Okay. So higher order programming is used for building data abstraction. Okay. And then we saw that there are two main kinds of data abstractions. So this is fundamental, and if you look at the mathematics of data abstraction, you can see that these are the two fundamentally different ways of building data abstractions. So objects and abstract data types. And you will see in programming languages that usually they're mixing them. Like, for example, in Java, you have integers, like 1 plus 2. Well, the 1 in Java is not an object, okay, it's an abstract data type. But you also have an object version of the integers. So Java kind of is not doing it very elegantly. But you have another language called Smalltalk, where everything is an object, including the integers. So if you do 1 plus 2, you're actually sending a plus 2 message to the object 1. Okay? So, and integers are also objects. Okay? So that's a design decision. Okay? And we saw, so I'm going to go over, I'm not going to show you this, run this code, but I'll show you how it works to make a picture. So we had an example of a stack, where you can create a new stack, you can push and pop elements, and you can test whether it's empty. And you can define it either as an abstract data type or as an object. So it's actually really interesting to see how the stack works as an abstract data type. How does the encapsulation work here? It works using a kind of cryptographic function called wrap and unwrap. Okay? So these are special functions that we will define in this course. So if you want to do a push of the stack, you push X on the stack. You basically, so W is the stack, which is wrapped. So this one is hidden. You cannot look inside. So you basically unwrap it, which gives you the stack, S. Then you can compute X bar S, and then again, and then you wrap it to return the result. Okay? So the wrap and the unwrap are what hides the outside from the inside. Okay? So the W is a kind of cryptographically hidden version of the stack. Okay? So all of these functions are defined like that. So the stacks are values, and the operations are done inside these boxes by using unwrap and wrap at the interface. Okay? So that's something we saw in the course, but in this course we'll go more into detail, and I'll explain to you how that really works. Okay? So another way of doing the stack is as an object. Okay? So the difference is that as an abstract data type, I have two things. I have stacks, which are the W's, and I have operations. Okay? Push, pop, and so on. And these operations are functions that take stack as argument. So you have two things, stacks and operations. Whereas in an object, everything is together. You have a single entity which combines both the operations and the data. So here's an example of the stack. Now I've introduced a new concept here called the cell. So I'm not going to explain that right now. I'm just going to tell you that the cell is like an attribute which you can assign to, and the push function will take this cell and take the value of the cell and add x to it and make an assignment. Okay? And the object itself is then a one-argument procedure which takes a message m, and depending on the message, push, pop, or is empty, will call one of these internal functions. Okay? So the object is just a one-argument procedure, and it takes messages. Okay? And it does what's called procedure dispatching. So you basically choose which operation to do. And the encapsulation is enforced by lexical scoping, okay? Your static scoping. The cell is only visible inside this function definition, okay? So that's one way of defining an object. So the object defined like this is very similar to object-oriented languages like Java. So most languages have a syntax for that. So just to refresh, this code will actually run. You can actually define it like this, but you can also see this code as a semantic definition, because this code, because we saw the semantics of all these operations, and you can easily translate this in kernel language. So remember, we saw in the previous course the semantics. So this code tells you everything. There's nothing hidden here, okay? It tells you exactly how the object works. It's the semantics. And the same for the stack. If I give you the wrap and unwrap definition, which I will give you in this course. Whereas most languages, they have a special syntax for objects. So the syntax kind of hides the semantics. So here is the Oz syntax, which is a little bit weird, but it's logical, even though it's weird. Class stack, attribute C, and you have a method, then the heading, and then the body of the method. So push X will do C, gets X bar, value of C, and so on. So all typical object-oriented languages will have some kind of special syntax. But the syntax is not the same as the semantics. The semantics is hidden behind the syntax, but the syntax is important because it guarantees that you're going to use the object in the right way, okay? So that you can only use the object in the right way by following the syntax, okay? Okay, so that's what we saw in terms of data abstraction. So we're going to see more of that in this course. Let me now go to concurrency, deterministic data flow. So we saw some concurrency in the previous course. We saw how the data flow occurs, okay? So you saw some of that. So let me refresh your memory on that. Concurrency is what happens when you have multiple activities that are executing simultaneously at the same time. And they're basically independent activities. So concurrency and independence are kind of synonyms. So the language has a new operation, a new concept called a thread, which creates a new activity, which is executing independently of the other activities. Okay? And most programming languages have a concept like threads. Okay? What we saw now, we saw how you do this with functional programming. So you add threads to functional programs, and you also have the unbound variables, the single assignment variables, and we saw how to make concurrent agents. Okay? And the way it works is by using a data flow concept. So data flow is a very powerful way of doing concurrency, which is, again, becoming more and more popular, mostly through big data analytics tools. So if I have two threads, and they share a variable, so x is an identifier, refers to a variable, so these two threads will share a variable. So the first thread will bind the variable to 1, and the second thread will do an operation, x plus 10. So these two threads are running independently. So we don't know which one is running first now. We don't know. But no matter what happens, the program will always display 11. The result is always the same. But the threads, they don't know that they're running in order. Each thread is doing its own thing, okay? So maybe I do x equal 1 before x plus 10. Fine. But maybe I do x plus 10 before x equal 1. Fine. So how does it work? It works because of data flow. So data flow is a very important concept. Okay? Data flow means that the computation waits until the data arrives. Okay? The data drives the computation. So here I have the two threads, I call them activities, activity A and B. This one is doing the addition, this one is doing the binding. Now assume the first activity is running first. Maybe it does. We don't actually know. The system is free to run the threads any way it wants. Okay? So if I try to do x plus 10, and if x is not bound, then data flow tells me that the operation is going to wait. It will wait until the data arrives. Okay? So the first activity will stop here at point 1, and it will wait. And the second activity also is running. And eventually the second activity will do x equal 1 at point 2. And when that happens, activity A, which is waiting for x, can continue. So you see, the two activities are kind of coordinating because of the data flow. Okay? And it's a very, very disciplined coordination because the variable is single assignment. There's only one condition. The data is either available or it's not. Okay? So no matter which activity is running faster, if A is running faster, it will wait until the data arrives. Whereas if A is running slower, maybe when I do x plus 10, x is already bound to 1. Okay, well that's okay. Then I just do 1 plus 10. And I don't wait. Okay? In both cases, I will display 11. Okay? In both cases, I will display 11. So that means the result does not depend on how the threads are executing. This is very important because threads are messy things. If you use threads in Java, you have to be very careful because if I have a state, if I'm updating a variable with two threads, it's important which one is doing first, okay? But here it doesn't matter. So in the data flow case, the threads are still behaving very nicely. Okay? So that's very important. And this is leading us to the data flow concurrency. Okay, and what we also saw in the previous course is how to do multi-agents. So here's an example of a pipeline, a producer-consumer. So the producer and the consumer will run their own threads. Okay, thread. And you basically have a pipeline. So the producer will create a list. But it's not a complete list. It's a list that is a partially constructed list. Okay? So it will be built incrementally. 1, 2, 3, 4, and so on. Okay? And the consumer will read the list using a case statement. So we have data flow again, like in the previous slide. Huh? If I do the case, and S is unbound, the case statement is just going to wait until the S is bound. So you see, automatically, the consumer will very nicely wait for the elements to arrive. So this gives you a very nice data flow stream concurrency behavior. Okay? So then you just run this. Just run regular code. So here let me define a function. Okay, the producer that I showed you is going to go very fast. So let me slow it down by putting in a delay, which stops the thread for a certain number of milliseconds. So it delays the thread. So the output will be, so that we can actually see the result. S of H bar T then, and I will browse H. Let me do this another line here. Okay. So these are producer and consumer. So the producer is building a list. You can see the list never ends. There's no nil. So the difference between a stream and a list, maybe it ends in nil. Huh? You can end it in nil. So that means the stream is terminated. But sometimes the stream keeps growing forever and never ends. Notice that both of these functions are tail recursive. Okay? So the producer here is tail recursive. In the same way that the map is tail recursive, this one is also tail recursive. Okay. Let me show you the execution of this, because concurrency is very important. So I create a thread, I produce starting with 1, I have another thread, and I will consume. Okay, this one is actually a procedure. There's no outputs. S. So here I have a concurrent program. You can see the 1, 2, 3 for every second a new number appears. Okay. So here we have a concurrent program with 2 activities, and the stream is like a pipeline. Huh? So each time the stream gets extended, the consumer will read it. And notice the synchronization is perfectly nice, because the consumer will, if it goes faster, so these 2 threads are independent. Maybe one of them will go faster than the other, and I'll explain in a few minutes what it means. They don't know about each other. Threads are independent. But that doesn't matter, because if the consumer thread is faster, then it will use data flow here to wait until the next element arrives on the stream. Okay? So the data flow makes everything nice. Okay? So that's important, and that's something we're going to do to build lazy concurrent programs in this course. Okay? Okay, concurrent pipeline. So now, let me dive a little bit down deeper and give you a more fundamental explanation of what's going on here. Okay? So semantically, what's happening in these threads? So this is very general. Every programming language that's doing threads is going to be doing it like this. Okay? So this is generally applicable. So each thread will execute as a sequence of steps. So it has its execution state, and it's executing like a sequential program. So each thread is a sequential program. Okay? And they're independent. But they will be executing on one processor. Okay, so I'm not talking about multi-core. Multi-core is a separate concept that's orthogonal to this, that we can do to speed up the computation by dividing it into different pieces. Okay? Here I'm running on a single processor. So it's fundamentally what's happening. The processor, a single core, is executing one sequence. That means if I execute two threads on one processor, the thread executions will be interleaved. It means once I will do one and then the other, and then one and the other. But it's not synchronized. I can do many steps of T1, and then one step of T2, and then maybe the opposite. So they're not synchronized in any way. Each thread is doing on its own random steps of the processor. Okay? So there is a part of the system. So how is this implemented? There is a part of the system called the scheduler, which at every step it actually chooses which thread. So the scheduler has a lot of power, right? You can see that. It actually can choose which thread to execute at every instruction. So all concurrent systems are doing like this, and they all have a scheduler. And if you want this to be nice, the scheduler, it has to obey some rules. Okay? The first rule it has to obey is that it's fair, which means it cannot forget a thread. It has to give, it has to remember all the threads, okay, and execute them all. And in real systems, the scheduler is more complicated than that. It has time slices. This is for efficiency, because you can't have the scheduler choosing every single nanosecond, okay? Because it maybe will execute a big program to choose. So that will cause everything to slow down. So what happens is, the scheduler will say, this thread will execute for a certain amount of time, and then there's a hardware interrupt, and then the next one, okay? And also it has priorities, because some threads are more important than others. A thread that handles a packet coming in from the network is more important than a thread that's just doing computation, because that packet is not going to wait. More packets are coming in from the outside, so you have to handle them. So you have the notion of priority. Okay. Now, this leads to another concept. The scheduler has a power. It is choosing which thread. And it's not the programmer who chooses. The scheduler chooses, according to its own rules. Okay? This is called nondeterminism. A program is non-deterministic when it does an operation that is chosen external, which means it's not chosen by the developer of the program. It's chosen by another power. So the programmer is not all-powerful. The programmer is not God in his program. Because the scheduler is another God, okay? So there are multiple gods in this little universe, if you want to say it like that. So the choices of the scheduler is an example of non-determinism. So it's inherent, okay? Non-determinism is always present in a concurrent program. Of course, it can also be present in a sequential program, non-determinism. It doesn't have to be concurrent. As long as the program makes a choice, if it chooses between one or the other instruction. But in a concurrent program, there are always choices. Because, well, you need at least two threads. If you have one thread, it's not concurrent. But But if you have at least 2 threads, there's always a choice. So it's by definition non-deterministic. Threads are independent. The scheduler makes its choice outside of the control of the programmer. And this, in particular, it's inherent whenever the program interacts with the real world. Real world events are outside of the control of the programmer most of the time. I type a key on that keyboard, the program, it sees this event arriving and it has to treat it. And it's not controlling that, so I am making the event. Okay? So this is a very important thing to understand. What is non-determinism and why is it inherent in a program that interacts with the real world? They can happen at any time, okay? And they must be handled when they occur. Okay? That means that if you want to handle these events, your program basically has to be concurrent, okay? Because they can happen at any time and the program has to handle them. Even if it's doing something else, it's doing something, and then this event happens. Well, you have to handle the event. That means it's another activity compared to what the program is normally doing, okay? Or maybe the program is doing nothing and it's only waiting for the external event. That's possible too. But usually programs always have their own little activity, even when nothing is coming in. Okay, and we saw an example of that. So this is a very nice example because it kind of crystallizes the whole issue in a simple and very useful example. Okay, this is not the only example. We see more examples in this course. But we saw client-server. So a client-server is it has to be non-deterministic, if you want to do it. It must be non-deterministic. If you have at least 2 clients, and you can prove that mathematically, okay? It is based on the specification of the client. When the client makes a request to the server must respond in a timely fashion that depends only on the network travel time and the computation time of the request. That means when I'm talking to the server, it has to respond based on what I am asking, not on what somebody else is doing, okay? Otherwise, this is very reasonable, huh? Otherwise, the system is not going to be satisfactory. If I make a request and the server does not respond, I'm going to be unhappy. And if this system is Amazon, I will not buy the thing, and Amazon will not make money, okay? So servers have to respond in a timely fashion. Okay, fine. That's reasonable, huh? You see that that has to be like that, huh? When I have many clients, each client makes a request, and the server has to respond reasonably, in a reasonable time. Okay, so what if you have 2 clients? They're both making requests. Okay? Client 1 makes a request. Client 2 makes a request. Which one arrives first? We don't know. It depends. Maybe client 1 is faster, or client 2 is faster. Maybe the network is faster between 1 and the server, or maybe it's faster between 2, or maybe there's congestion. It depends on many things. So you cannot determine the order in advance. You see that, huh? Depends on the precise timing. So the server, you don't know which client request is going to arrive. It's either 1 or 2, if there's 2 clients. And you don't know which. So this is non-determinism. Because you have to treat the first one that arrives. So you don't know which one it is. The programmer cannot predict it. Okay? So the whole client server is non-deterministic. Okay? See that, huh? It's non-deterministic even if everything else is purely functional. This point, right here, where the server listens to the world. That point is a point where you have to make a non-deterministic choice. See that, huh? This is a subtle thing, and but it's very simple. Okay? Okay, very good. So we have to do it. We have to write this program that's non-deterministic. Okay? And the problem is, it has to work correctly for all possible non-deterministic choices. There might be an exponential number of them. If I have n clients sending messages, there are n factorial possible orders in which they can arrive. And it's actually much more than that, because a program like Amazon server is running for a very long time. So the number of requests is basically unbounded. So the number of choices is incredibly large. And our program has to be correct. We can't test them all. It's too many. Testing is important, but you can't test them all. So what do you do? Well, you have to be correct by design. The design of the program has to guarantee the correctness. Okay? And that's one of the things we're going to talk about. How do you live with non-determinism? Okay? Okay? So that's one of the themes of this course. How to live with non-determinism. And you have to tame it. Non-determinism is like a demon, okay? That's very powerful, and you have to tame this demon. That's one of the hardest things for a programmer to do. It's hard in a concurrent system. It's even harder in a distributed system, okay? So there's another course I'm teaching, which is called LINFO1131 which takes this to the next level. Because here we have a distributed system, which is running on many computing nodes, and they're sending messages to each other, and you can have failure also. So there's a new thing here that nodes can fail, which makes it even more complicated. Okay? And all of that possibilities have to work. You see, it's not so simple, and the only way to do that is to make it correct by design, because you cannot test all problems. Okay? So how do we do it? Well, we have already one solution: deterministic data flow. This is actually solving the problem by design. The non-determinism is hidden because of functional programming, because this is functional. Even though the scheduler is doing non-deterministic choices, the results are always the same. So this is the best, if we can do it. Huh? The problem is we can't always do that. But we have to do it as much as possible, because this one, the problem basically goes away. That's very nice when the problem goes away. Huh? So we try to do this as much as possible, because it will make the problem go away. But the problem cannot always be magically made to disappear, because some non-determinism is essential, is based on the specification. Like the client-server case, you cannot magically make that go away, okay? Because it's inherent. That means there is some minimum amount of non-determinism that you have to solve, okay? And so that's what we're going to see in this course. How do you master that? And how do you reduce the non-determinism? Non-determinism is really nasty, huh? I don't know if you've ever really had to solve a non-determinism problem, huh? I know that because I have, for example, we did research in distributed algorithms, and sometimes there is something non-deterministic. And so the poor PhD student, because it's usually the PhD student who's doing the work, is spending days and days trying to figure out why is it not working. There's some little thing that's not deterministic, that's above. And big systems on the internet, like Google Search or Amazon or Facebook or Twitter, well, X, those things have very complicated programs behind them. And they have very smart engineers babysitting those programs all the time, day and night, okay? And those engineers are sometimes very, how do you say it? They get lots of gray hair very quickly, okay? Because many of the systems are not written in the right way. They're not following this paradigm because they were written a long time ago. So what I will try to do is tell you the best way to do this kind of thing, so you will have the least amount of gray hairs in your career, okay? Okay, so that basically refreshes you. So now you're up to speed, okay? So we're not going to talk so much about semantics or lambda calculus in this course, but we're going to talk about mastering declarative programming. So mastering nondeterminism will be a main theme of this course, okay? And next week, we will start talking about, well, it won't be next week because next week is the 27th, which is a holiday. So please enjoy the holiday. But there will be a lab session the next 2 weeks, okay, 2 lab sessions. And then the next lecture will be in 2 weeks, and I'll start talking about lazy evaluation, which is a powerful extension of declarative programming. It's a really neat thing, and it's a very new thing that you haven't seen before. Okay, so let me end there.